Alt, the executive director with ADMC. I've been with ADMC since 2018. Previously, we used to offer these courses for about 5 or 6 years, from I think about 2011 to 2017 in person. NRCS does recognize ADMC drainage water management certification as part of their technical service provider training program. We're glad we can still do that. I will mention that today's class is funded through an agreement that ADMC has with CTIC out of Indiana through a contract with EPA to provide some of these trainings. Quick background on ADMC. We are a member-led organization. About half of our funding does come from our supporting companies. We have a lot of the big tile manufacturers are on our board in our membership base, as well as some of the engineering groups, the contracting organizations that are out there, and others that have interest in water management. A lot of the work that we do is a lot of educational outreach and trying to figure out ways to better implement the suite of conservation drainage practices. We were actually involved in a few of the bigger projects here in Iowa recently, the Polk County Saturated Buffer Project, which I think some of you may have heard of in the past. But we were able to install 51 of these edge of field practices in about 1.5 years in central Iowa. And now we're kind of making this model modular and moving it forward. We probably expect to get 200 to 300 sites in a year in Iowa here moving forward in the very near future. So we're hoping to take that show on the road. Now we're kind of revamping this drainage water management certification course, hoping that we can do the same to get drainage water management to scale. A little bit about our certification today. NRCS does recognize our drainage water management certification, but I will caveat that with the change to the DIA 164, so Drainage Implementation Activity. For those that are familiar with the NRCS system, this used to be a CAP program, CAP 130, which was a planning activity and not a design activity. With the change to it being a design activity, it's based on each state's code. So there is a PE stamp requirement in addition to either this certification to become fully TSP certified. So I encourage all to check with their local state conservation engineer to make sure they know if they need to have a PE stamp or not to go with this. Even without becoming fully TSP certified, we think there's a lot to learn within this course. Today we will be giving some pre-test for each session. So there's 3 sessions that'll have a pre-test and then a final test at the end. With that final test at the end, we're requiring a 75% success rate on that test to receive that final certificate. We don't think it'll be too challenging, especially if you pay attention all day to Gary's excellent teaching here. We are hoping that this is interactive. With it being online, that's a little bit difficult, but we will be doing some polls throughout the day. Gary's hoping that you'll interrupt him with questions to raise your hand. And to kind of go over some Zoom basics, I'll do that in the next slide here, but we do hope you stop Gary every so often to ask him questions. For any CCAs or PEs here, there are some CEUs available for these sessions. We will hold up the QR code scanner at the end of the sessions for those that are hoping to get those CEUs. Right now, let's see if I can do this on my opening Zoom day, but we're going to launch a poll just to see how familiar everybody is with the drainage water management practice. So if you see that poll, go ahead and please respond. We'll give you a little bit of time here to take that and respond. I will caveat this with, of course, being our first online attempt of training this course. There is a Midwest-wide outage of MediaCom, the internet provider, where I co-work out of, and so we're on a backup system. So if I get glitchy, please let me know. I may have to turn off my video to make sure everything goes smoothly. Gary is the co-host though, so if my internet goes out, he'll be able to cover it for us. All right, we're still getting a few responses in. All right. So hopefully everybody can see the results now of this poll. So we do have 3 people that could probably be teaching this course, so we might be calling upon them later on if Gary's internet cuts out on him, because I definitely cannot be teaching this course, I don't think. So that's good to know. We have some backup online, so feel free to jump in if needed. But yeah, that's kind of what we expected. A lot of people, have been introduced to drainage water management, but are definitely willing to learn more, and we think you will throughout this course. And we are excited to see that there are some newcomers to the practice and are wanting to learn. All right. So just some Zoom basics with a meeting of this size. We are hoping that our guests, you stay muted unless you do have a question. There are some controls at the bottom of your screens. That reactions button at the bottom of your screen looks like a little emoji right now. You can click on that and there's a raise hand function. Hopefully either Jean or I will see that and we can call upon you or get your question answered. Otherwise, there's the little conversation balloon down there for the chat, which we'll have you work on the chat here shortly, that you can enter your questions directly into the chat, and I'll interrupt Gary at an appropriate time to have him answer that. The lower left, there's just your mute button. And same way, if you want to share your video, it'd be great to see people's faces, especially if you are talking throughout the day. I kind of mentioned before, we might have a few internet issues today. We're hoping not. But if it does crash, Gary is the co-host and he's on a pretty reliable network. So the meeting should go on without me. We will be putting those quizzes, they're a Google form. So there'll be links to the quizzes that will be placed in the chat. And with that, to get comfortable with the chat feature, and kind of introduce people to each other. We're hoping that you enter your company and maybe your location where you're based out of. It's pretty exciting to see where all the people that have signed up for this meeting are coming from. We think that might build some camaraderie and maybe make some connections for everybody in the crowd. So while you're entering your information, if you want to, into the chat, I'll introduce our trainer for the day. Dr. Gary Sands is a professor and extension engineer out of the University of Minnesota. We're really excited to have Gary back teaching this course for us. Gary kind of worked with ADMC on the original drainage water management certification courses. He's been doing drainage management for quite a while, has led a lot of the extensive research there up at the University of Minnesota, very familiar with the practice. And as you'll be able to tell, he has a knack for teaching the basics and teaching how to get these things installed. So with that, I'll stop sharing my screen and get it turned over to Gary.
Remember to unmute myself. That's the most important thing of the day. Good morning, everyone. Thanks, Keegan, for the handoff there. Quick shout out to Jean Hansen as well. Jean's out there in the background somewhere, and she kind of keeps the wheels going around, keeps them on the bus in this organization. So thanks for everything that you do, Jean, as well. Yeah, my name is Gary Sands. I've been at the University of Minnesota since 1998, so a few years now. I have an extension role here, so I'm a professor and extension engineer. I teach both in class on campus and also in the extension mode out and around the state and around the region. We have quite a strong extension connection collaboration across the Midwest and actually across the US with regard to drainage water management and practices such as this. So I'm an agricultural engineer by training in the what we used to call the soil and water area. And so that's sort of the discipline that I bring to these topics. Just glancing at all of the locations and connections that all of you are posting in the chat. As I was watching that scroll by, I saw somebody from University of Delaware, my alma mater. That's where I started my my university, my post-secondary education. So great to see the mix of people from all over here. Also great to see a mix of backgrounds and levels of knowledge And as Keegan said, nice that some of you have enough knowledge maybe to step in and do some teaching. And so, as Keegan said, if my internet goes down, we may call upon you to help out. I'm going to go ahead and share my screen here, and then start the slideshow mode. Just give me a second. All right, you should be seeing my title slide here, and I'll hope that Keegan will let me know if that's not the case. Let me just get my screen oriented here as well. I've got the participants window open. I want to open the chat window so I can see conversations going on there. Great. So as you know, as Keegan mentioned, we've got a lot planned for you today. We've got 3 full sessions here. And I just want to acknowledge that this is ambitious, in an online environment to have this much content in one day. And we know it's going to be tough. And the degree to which we can interact with each other, I think will help kind of break up the day and make things flow along and make it a lot more fun as well. And so, from time to time, I'll ask questions. Usually when I ask questions, I wait for answers. And again, we can use all the tools here. We can use the chat window to respond to things that I might ask or a question that you have. As Keegan mentioned, the reactions button down there, when you click on that, not only can you raise your hand with that, but there's also an affirmative response, a negative response. You'll see there, yes, no's. So I might ask some questions like that. Is this an example of a sandy soil or a clay soil? And you can respond in that way too, and we'll get a sense of what we're all thinking as we go along through, and that'll just kind of keep it fun and light. I'll try to take some stretch breaks. This first session is designed for a couple of hours. And we'll take a formal break, at the end of that, of course, but we'll take a stretch break in the middle too, just to give ourselves a chance to, again, to stretch and keep alert. Let's see what else as we get going here. Yeah, I guess just let me also say that I think Keegan mentioned, I've been had the pleasure of working with ADMC since 2011, I believe, on setting up these trainings. And so we've learned a little bit over the years in doing these, but there's always room for improvement. We'll have an evaluation either at the end of the day or shortly after the event here, and we're hoping to hear about your thoughts on what went well today and what things we might be able to improve on going forward. So I hope everybody sort of has a good orientation to Zoom now, and you know where things are, you know where the chat window is, you know where your reactions are, and we can go ahead and get started. The first session is really going to focus on soils and drainage, some traditional drainage concepts. And you might think, wait a second, we're here to talk about drainage water management. Why are we going to spend time here? And basically, we want to do this because this is where the science of this work lives. It lives in the basic drainage science of drainage, how drainage works, and of course, that all depends on soils and soil properties and soil physics as well. So this is going to provide a nice foundation for what we talk about later as we get more into the practice of drainage water management. And so that's why we start here. And to begin, we're going to begin each session with kind of another quick poll question. And so Keegan, if you don't mind launching that for us. So go ahead and take a minute to answer this question. How important is soil type when planning a drainage system? Go ahead and respond to that poll.
And Gary, I can't remember if you can see the results coming in on the polls, or is that
I
just
can.
me?
I
Okay.
can see them, and I'm right in there with all of you. About as important as a morning cup of coffee. Soils is crucial to our understanding of how things work here. So go ahead and close that, Keegan. And the other thing we're going to do, and Keegan mentioned this, is as we get into each session here, we're going to start with just a handful of pretest questions. Again, we're interested in knowing sort of what knowledge you come into this with, and again, we'll have a post test at the end of the day to hopefully measure some learning that's taken place throughout the day. Keegan has posted a link to these questions in the chat. So if you look at the chat window, click on that link and take just a couple of minutes to answer those questions before we dive in. And for practice, go ahead to your reactions and give a thumbs up if you've completed those. Okay, we'll go ahead and move along, and go ahead and finish those up if you haven't yet. Subsurface drainage and soils. Let me preface this content by saying I am not a soil scientist, but soil has been absolutely very basic in terms of my background in agricultural engineering. Couldn't do most of the work that we do without some kind of understanding of soils. So here we go with some basic soils. I'm hoping many of you had the opportunity to have a basic soils course in school. Unfortunately, that's we don't see a lot of that anymore. Even at the University of Minnesota, we used to have a soils degree, and we don't anymore, but we still have the courses there. So, basic soils are a mixture of stuff. It's rocks, it's bugs, and some void space. So the mineral fraction of our soils is of course where the sand and clay particles and so forth come from. The organic matter is really the life of the soil, and that's what makes our soil so productive, that biological activity. And of course, that these fractions that I'm showing here can range quite a bit depending on soil. These are just sort of representative values. And the void space is where the air and water resides in the soil. And it's not 50% for every soil. As we'll see here in a second, that amount varies depending on soil type. And at any given time, of course, that fraction of air and water in the soil is a reflection of the moisture content of the soil. And the mineral fraction, of course, we see, from coarse sands all the way down to clay. You don't know if you can see it, but that tiny little clay particle at the very bottom here, let me turn on my pointer, right here. This is just sort of a representative relative sizes, one particle next to another. And the interesting thing about soils is that, clays are so reactive and so different than all the other soil particles. And it's one way to think of this is, if you had a bucket of sand and you added 1 teaspoon of clay particles to that bucket, you would completely change the properties of the soil in that bucket. Clay is so interesting the way it functions in soil. Porosity is a measure of this void space or pore volume in the soil. Okay, and so that's a term that we often use to describe our soils, the amount of pore space in the soil. And I draw a lot of pictures and cartoons in my presentations. Hope you find them informative. But here we're looking at a soil in various stages of wetness. So on the far left, you see a soil, and these are soil particles here in brown that is completely saturated. And then as we move to the right, we see a soil at field capacity. I hope you're familiar with that term, field capacity, and you see those drops of water here leaving. This water will freely drain from the soil if it has an opportunity to do so, to move from saturation to field capacity. At field capacity, there's still a lot of water in the soil. And as we move then and get drier to the right, we approach wilting point, and the soil can even get drier than that. But at that point, there's so little water, it's adhered to the soil property, to the soil particles. It's impossible for the plant to get at. And so the plant, whatever we're growing here, is happiest in between field capacity and wilting point, much closer to field capacity as possible. So again, field capacity is that term we use when natural drainage or artificial drainage has ceased. We hope our soil is at field capacity at that point. And drainable water, again, is that fraction of water that's going to freely drain from the soil, represented up here by the bar on the top. All of that drainable water is happening, again, here between saturation and field capacity. Plant available water is another term that we use to talk about soil moisture. And then, again, that's typically between field capacity and going toward wilting point. And that's where the plant is the happiest. As I mentioned, these characteristics change quite a bit depending on soil texture. The drainable porosity, if you look at the percent by volume there, is very low for clays, and it's very high for sandier soils. And then you probably know then that the available water in a soil, the plant available water, is just the opposite as drainable porosity. So your clay soils, your tight soils will have a very high amount of plant available water, but a low drainable porosity. And the opposite is the case for a coarse texture soil, sandier soil, where they have a low amount of available water and a high fraction of drainable water. So those two things work in opposite, depending on soil type. Now this looks complicated, but bear with me for a second here, and I'm going to turn on my little annotation tool. the soil moisture characteristic curve, and I hope most of you are familiar with this, but this is just a way that we graphically express the way a particular soil holds on to its moisture. And also it's a way of looking at the drainable water fraction of a soil and the available water fraction of a soil. So down here we have moisture content. Let me turn on my annotation here. We have moisture content here down here on the bottom, and we have pressure over here on the left. And so we start out down here at the bottom of these curves, and this is where the soil is saturated. So you see this 40, 45, and 50. That's really your percent. That's really your pore volume of the soil. And so we see a higher pore volume for a clay, a lower pore volume for a sand. And then the difference between saturation and field capacity, this difference right here, again, that is your drainable water for that soil. So as we mentioned, for a sand, we have a lot of drainable water. You want to move a water table in a sandy soil, you've got to move a lot more water. And compare that to the same thing for the clay, we have a much smaller amount of available water, or excuse me, of drainable water. Now the available water is just the opposite as we look at the difference between wilting point up here and field capacity right here. This part of the curve describes the available water. So that's larger for the clay, a little bit smaller for the loam, and even smaller for the sand. So again, as you know, those sandy soils are droughty soils. They don't have a lot of available water, plant available water. It's higher as the soil becomes finer and finer and more clay there. So it's good to know our way around the moisture characteristic curve. Again, maybe some of you have experience with developing these curves in the laboratory. It's a fairly easy thing to do. We bring in soil samples and we apply various amounts of pressure to them and measure the amount of water that comes out, weigh the sample and so forth. And so it lets us express how much moisture is in the soil at various tensions or pressures. And we'll see in a second here that this is quite important, because as we start looking at water table behavior, it's important to keep these concepts in mind. What is a water table? This would be a place where, if we were in person, it's a good place to stop and have a discussion about what does the concept of water table mean to you. And I'd be happy to have you throw something in the chat if you can think of a quick phrase. How do you define a water table? See if we have any brave souls. One thing I've heard people mention is, well, if I go out and dig a pit, and if there's moisture in the soil, it rises to a certain level. It may rise to a certain level in that pit, and that's how I know where the water table is. Water surface below the soil, natural level of water. I'm just reading some of the stuff in the chat. Natural level of water below the surface, where the water remains perched in the landscape. Yeah, these are all correct. And let's get just a little bit more technical. And let's perhaps make it add something to the image here. Now we're going to add a tile. I don't know why the tile is pink, but it is today. We're going to add a tile to this system. And let's imagine that this soil is drained by this tile, and we're catching it right at the moment where drainage stops. If we could kind of do a freeze frame right there. And let's make a couple of observations. The gravitational water drains from the larger pores. The largest pores drain first, Smaller pores drain after that because water is held more tightly there. And as we know, as many of you know, water table drops from over a matter of minutes or hours to days, depending on many factors, soil type primarily. So thinking more then, and again, thinking about what a water table actually is, what is the moisture content? Again, as we do a freeze frame right now, what is the moisture content of the soil below the tile? Go ahead and throw something, seems like an obvious question. Throw something in the chat as we think about this. Saturated, saturated, saturated. That's right, saturated. Moisture content below that tile. We have saturated soil below the tile. What is the moisture content in the soil above the tile? Between wilting point capacity and field capacity, field capacity, field capacity. And yes, there was a question, post-gravitational flow. Yes, gravitational flow has stopped, and we did a freeze frame right there. Someone said we put field capacity on the quiz and missed it. It's a little bit of a trick question because the follow-up question to that would be, well, exactly where above the tile? Do you mean like right above that saturated soil? Or are you asking, am I asking midway up? Are we asking at the field surface? And the point of this question is that the moisture content above the tile is not a single value. You can imagine we have saturated soil at the tile and below. Right above that, a couple of hairs shallower than that, that soil is still almost completely saturated. And as we go further up in elevation or further up toward the soil surface, it's less and less saturated. Till we get, if we get far enough away from that water table, we may in fact be at field capacity. So we're going to have a range of moisture contents in that soil above the tile. And I think many people might think that, well, after drainage, after gravity flow stops, everything is at field capacity, and that is not the case. Well, full disclosure, I said I'm an agricultural engineer, so I like to think about pressures and technical things. Again, as we think about this concept of a water table, it has something to do with the pressure in the water, in the soil. What is the pressure at these various places? Let's start with right at the water table. If we can say that we have a water table right at the depth of the tile, what is the water pressure right there? Anybody want to venture a guess? Atmospheric. Atmospheric, that's right. Atmospheric pressure or zero pressure gauge pressure. It's atmospheric pressure right there. Okay, let's start with the easier second question then. As we go deeper, what is the pressure in the water? Is it stay atmospheric? It gets higher. Below that, as we get deeper, we have pressure just like a swimming pool, hydrostatic pressure. As we go deeper, we have the pressure increases with depth. Pretty logical. Now, as we go shallower, what happens to pressure? If we start at 1 atmosphere, atmospheric pressure at the water table, as we go shallower, what's happening to our pressure? It's lower. It's going to be below atmospheric pressure. And so often when people are talking about this soil moisture characteristic curve, they're talking about water intention. They're talking about water held at pressures. These are at below atmospheric pressure. So as we go above the water table, water is at less than atmospheric pressure. And that changes again linearly as we go upward in depth. And the property, the amazing thing about really it's the amazing properties of water is what makes all of this happen. What makes it so cool. And none of this would exist without the attractive forces that water molecules have for one another, and that is displayed in surface tension. And so the interaction with surface tension and soil properties is an amazing phenomenon, and it's what allows water to cling to those smaller pores and be held more tightly in those smaller pores, and it sort of makes this whole system work. So keep that in mind. And sorry, I kind of nerd out on this stuff, but you learn that about me pretty quickly here. So again, trying to kind of couple these things that we've been talking about here for the last couple of minutes. Here's our image of the soil profile where the tile is. Water has just stopped draining, and now we can look at our soil moisture curve again. And again, we start down here at saturation, essentially the porosity of the soil. And as we go upward here now, the soil is drier and drier. And for any given soil, we can just take that moisture characteristic curve and put it right on that scale. And that's going to tell us, again, with depth, what we can expect that moisture content to be as we go toward the soil surface from the water table. Well, guess what? I mentioned that pressure changes linearly with depth. And we're not going to get to field capacity until we're at, let's say, 1/3 of a bar here, or 130 inches. So our water table has to be like 130 inches deep to get to field capacity at the ground surface. And we think, wait a second, our soils are well drained. They drain well with tile. We got to be getting closer to field capacity than that. Well, of course, our plants are pumping lots of water out of the ground and moving that curve over very quickly. Evaporation, transpiration, evapotranspiration. We're also getting more seepage. And so we start shifting that curve away from that freeze frame where drainage just stopped to a drier soil profile. And all those things work in concert to get the kind of moisture contents we need for good trafficability and good crop performance. Well, let's look at this in a sort of a simpler way here. So what we're really saying is that, again, this is still our basic units, still our basic axes for our soil moisture characteristic curve. We have moisture content here, and we have height above the water table or pressure. So we're at saturation at the water table. And as we go up toward the soil surface, we see a higher percentage of empty pores and a lower percentage of water-filled pores. So our soil is drier and drier as we go toward the soil surface, wetter and wetter as we get down closer to the water table. If the water table is deep enough, we may get to field capacity by the soil surface, or we may not. But soil type matters in a big way. So here are two different soils on the left and on the right. Think about this curve that you see here as the soil water characteristic curve, essentially. It's what that is going to look like for that particular soil. So my question to you is, one of these is a sandy soil, and one of these is a clay soil. How many of you, using your affirmative response or negative response, think the soil on the left is the clay soil? Yes or no? Is the soil on the left a clay soil? And you can use your reactions if you want to. You'll find a positive and negative button there. or the thumbs down. The soil on the left, you're all correct, is the sandy soil. And the soil on the right is the clay soil. So look at, just in a relative way, the difference between those two. For a water table at the same depth, we're likely going to have a wetter soil for the clay soil than the sandier soil. I think that's kind of intuitive, if you will. Now let's look at the influence of water table depth on this whole thing. Now we have the same soil, and this looks like it's reflective of the sandy soil. We have the same soil here on the left and the right, but at a different water table depth. This curve on the right, this is the exact same curve as we have over here, but it starts at a shallower level in the soil. So we're really just looking at this same curve, but it's kind of chopped off right here, you see, because we have a shallower water table. So shallower water table here on the right, even though we have the same soil left and right, means that our soil above that shallower water table is going to be wetter. We're going to have more of it filled with water than is the case on the left where we have the deeper water table. So I know that you kind of know this intuitively. Shallower water table, we have a wetter soil profile above. The take home here is that I don't want you thinking that, oh, I could hold a water table at 1 foot below the surface and my soil is going to be a field capacity in that top foot, or 1.5 feet or 2 feet. It's not the case. It's going to be wetter than it would be if the water table were at 3 feet or 4 feet. That's the take home message here. And I'm showing you these curves and graphics here to kind of give you a foundation to understanding why that's the case. So if we put together both soil type and water table depth, then it really becomes interesting to look at this. So here's our sandy soil on the left and our finer soil on the right. And now let's elevate the water table like we do with drainage water management. And now we have to shift our water curves again to start at saturation at the water table, and then going up according to the soil moisture characteristic curve. And now look at the difference between these two soils. And so the finer texture soil, which are typically the soils that we need to drain, that need help with natural drainage, when we maintain shallower water tables, we are really accepting that we have a much wetter soil profile above that water table than we do for a coarser soil. So it becomes more critical to look at how we're managing the water table in finer texture soils, because we know that we are really adding some risk into the system by maintaining a wetter soil profile with a shallower water table. So that's what this all sort of boils down to. I'll just pause here for a minute and ask you if there are any questions about this. And feel free to throw something in the chat, raise your hand, digital hand. I can't see many of you in terms of the videos here, so I can't see if you're physically raising your hand in front of the camera, but feel free to raise your digital hand or throw a question in the chat if you have one. Okay, let's move on then. And Keegan, please keep an eye out for me because I may not see a question if it pops up. So I told you I like to geek out on this stuff, and everything up till now has been a discussion of static soil water. The water's not moving. We did our freeze frame right after drainage stops. We didn't really talk about water movement in soils. This is also very interesting to look at. If we could imagine a soil profile here that's completely saturated, it might look something like this. And if we were able to just in an imaginary world, just kind of punch a tile in there and catch it just before drainage starts, as we're seeing right here now, and then turn the drains on and see what happens then. What first happens is that a pressure field is set up. within the soil profile in this saturated soil that looks like something like this. Okay, so these lines are constant pressure lines that emanate away from the tile and increase as we go away from the tile. And so we know that water flows downhill, or it flows down gradient from high pressure to low pressure. What is the driving force? Why does water enter into a tile in the first place? How does it do that? Once a tile fills up, isn't the pressure in there the same as the surrounding soil? How does water flow into a tile anyway? What is the pressure inside of the tile? Let's say right at that moment, if we were able to just punch it in there and again do a freeze frame before drainage even begins, what is the pressure inside the tile? Atmospheric pressure. Atmospheric, that's correct. It's exactly right. It's atmospheric pressure. If we've done our job right in terms of the tile installation, it's atmospheric pressure. And the pressure in the water surrounding the tile is going to be greater than atmospheric pressure. So again, it's that hydrostatic pressure that's moving water from surrounding the tile into the tile. And when that happens, we get these flow lines that occur. And have any of you heard people that work with these systems in the field talk about how most of the water in a tile enters the tile through the bottom? And that's in fact what happens. And these flow lines, again, it's just a simple graphic, but it kind of depicts exactly what happens here. So most of the water is kind of flowing down deep up into the tile from the bottom, because that's the way the hydrostatic forces are working here. As this soil is drained and that water table becomes deeper and deeper, this flow net here becomes squished and everything changes in shape, but the same principle applies. And then of course, once the water table drains down to the tile, we no longer have those driving forces, and that's when the flow will cease. Here's just a screenshot or a picture out of a textbook showing one of these sort of ant farm models, some sand and then dye injected into that flow field. This is the saturated surface right here. And we can see these flow lines traced out. If this model were actually taller, we would see these flow lines here go very, very deep. They're cut off, of course, because they can only go so deep. That's the bottom of the model. And so Christensen's have shared that in a saturated buffer, it's a question, does the water also mostly flow out of the bottom of the distribution tile? So in a saturated buffer now, we're sort of reducing, or we are reversing the flow and getting flow to move from the tile into the soil. And I have not thought about that until you asked that question. So that's a great question. Does anybody want to take a crack at it?
I want to hear Laura's theory.
Yeah, I'd love to hear Laura's theory.
Can you hear us, Keegan?
Yep,
Can hear you
good.
very well.
Okay. No, I just asked because I was reviewing a paper and someone made that claim that most of the flow would be from the bottom, and I questioned it. So I don't have an answer, and that's why I asked you, Gary.
Yeah, my gut feeling is that in a situation, and of course, apologies to the rest of you because you might not be on the same page with what we're even talking about here. We'll make a few comments about saturated buffers later, but my intuition says that I don't know, we might get more of a uniform movement of water from a tile around all sides. Of course, it's going to depend on that pressure field around the tile. But my guess would be, again, my gut would say, we're not going to be pushing most of the water out of the bottom of the tile. But, again, that's just off the top of my head kind of a response. now I have some homework to do. I'll draw some flow nets tonight and see what things look like. Great question though. Again, some basic soil stuff. You know, soils are categorized in lots of different ways. They're categorized in hydrologic soil groups, A through D, and there's some combinations as well. Typically, it's these groups C and D that are the challenging soils in terms of natural drainage. And again, this is just by way of kind of a quick review of soils, some of the data that's out there, some of the information that's out there, and how things are classified. Soils are also classified by drainage class, you know, frequency and duration of wet periods. And again, it's they're described in this way. It's typically classes, you know, 5, 6, and 7 are those soils that, again, are of interest in terms of providing some additional drainage. Tons of resources out there for soils data, and I hope those of you who are in the field working with these systems are taking full advantage of the ample soil resources that are out there now. They're so easy to get and to work with, and so you know, we don't have to shoot from the hip anymore in terms of knowing what soil is out there and what are the basic properties of these soils. The Web Soil Survey is still an excellent tool, and I got a couple of screenshots of that I want to show you. The Soil Web and ARS app that pulls from that same information, but has the advantage of you can pull it up on your mobile device when you're in the field and locate yourself and find the soil right there. You can also use it at your workstation, and it's another very handy way to get at soils information. The Illinois Drainage Guide, I haven't looked at it in a while, but it used to be a great source of information for soils information. And Mark, I see your comment there in the chat about flow in a saturated buffer distribution line. So I'd encourage the rest of you to take a look at that and you know, ponder that a little bit. Thanks for those comments, though. This Web Soil Survey is really an easy way to get at soils data you might need for your projects. I hope you're all familiar with this, but if you go to the if you just Google Web Soil Survey, it takes you right to this screen right here, and then if you hit the green button, it you jump right into it. And this is sort of what the initial page looks like. And when you get in there, if you click on the help right away, you're going to get a really nice, concise description of kind of how to walk through getting the information you need. Define your area that you're interested in looking at, view that information, explore all the different soils data that's available once you define your area of interest, and then you can develop a report and print that information up for you, your files, or your client as you go forward. So what I've done here is I've started with area of interest over here, and I've defined a field that we've done quite a bit of work on at the Southern Research and Outreach Center in Waseca, Minnesota, South Central Minnesota. That's this field right here. And I've just used that as my area of interest. And I go in there and I click on the area of interest tab or button, in other words, and just open up a rectangle around that field. And I'm calling that my area of interest for this example. And then you can pop this open. You can give this area a name, and then that flows over to your report later on. And then after you do that, you can start to explore all of the information, the soils information relative to that particular area that you've just defined. So I click up here on the soil map. That pops this up right away. I can click on these individual soil names here. My table here pops up right away. It tells me what soils are in the field and what percent of the field is in those particular soils. And you can start to explore all the different properties. As I go now over to the Soil Data Explorer tab, you'll see just tons of different hydric soil information, irrigation, construction, you name it, all the information that's there, it's readily available. I clicked on the hydric soils and just a moment here, I'm trying to move my something out of the way so I can see my screen. I clicked on hydric soils and I asked it to show me the hydric soils map, and it's showing me those soils that are rated as hydric versus less so. Then I can also ask to see the table of hydric soils or any other property that that I'm interested in knowing about. And you can explore all of that and look at that, and then head over to the soil reports tab. And just noting here that here's all the different kinds of information that are available to you, and there's some different inputs that you can provide there to to get the report, to get the kind of data that you need in the report that you're going to generate here. So you go to your reports here. Once you've set that up, you go to shopping cart and put in a couple of name the report and so forth, and then ask it to go to the checkout button. Now, even though this is set up like a shopping cart and checkout and so forth, this is all free. There's no cost to this, and you end up generating a soil report that is specific to your area of interest. And this, for those of you who are used to looking, going to the library to look at to find soil reports for your county, that's exactly what these look like. But now this is generated specifically for your area of interest. So again, a great resource for soils information that if you haven't used that, you might want to consider that. I mentioned the soil web. This was developed a number of years ago, I believe by the ARS. But again, it's getting at the same data, but it serves it up in a slightly different way. And again, you can have an app on your phone or your tablet, and if you have geolocation on, you can pull up your soil map for wherever you're standing. I've zoomed into using that into the same field now, and this is what using again the desktop version of this is going to look like. So this is what this looks like, and you can click on. I clicked on this particular soil feature right here, and up popped this table. I can then click on any one of these soil types. For instance, I clicked on the Webster, and it gives me some horizon information here, and you see all kinds of other information that I can also open up and look at. I can click on any of these properties, and it's going to tell me, at least in terms of the book values of what they are for this soil. And I click on hydraulic conductivity here, and up pops the hydraulic conductivity with depth, the saturated conductivity with depth for this particular soil. So again, you could have all of this, right in the palm of your hand, again, because it works on mobile devices. And it's very, very effective way of getting at soils information. This also works in Google Earth. Now, I used to use it in Google Earth quite a bit. I haven't used Google Earth in quite some time, but I know many of you might use Google Earth. I've seen, conservation staff and contractors using Google Earth to actually draw in features associated with various projects, sometimes even tile layouts, location of structures and things like that using Google Earth. And then you can bring in, you just do a search and you can bring in the soil web. If you look at my laser here over on the left, you can bring in the soil web layer into Google Earth and use that as a background layer for your work. And of course, you can click it on and off and use it however you need. Very powerful. So moving along here, just a quick review of some drainage design concepts. Well, I think it suffices to say that we're in a new age here of thinking about managing excess water. in our fields. And even though water still moves down potential or downhill, most of us know by now that we need to think about a new approach where we're considering both production objectives and environmental objectives. And if you haven't heard it before, the golden rule of drainage that was coined by our esteemed colleague, Dr. Wayne Skaggs. It does not go drain unto others. That's not the way it starts, but it goes drain only what's needed for production and trafficability and not a drop more. And so that should be our mantra as we go forward thinking about managing water in our fields. You know, we've taught basic drainage design workshops for many years, and I use this graphic to illustrate this iterative process where we gather background data, figure out if we have an outlet to take water to, and then we think about these various concepts as we develop a design for the field. We're not going to go through all of these, but just wanted you to see that it is not a simple process of developing a good drainage design for a field. And there are many objectives here, and I already mentioned production, environmental objectives, but there's some other objectives that come forward as well. Thinking about our systems, we want them to work well and be close to maintenance free as possible, minimize unwanted effects. And as we'll see here soon, we also want to be thinking about developing drainage designs for those fields that don't have drainage yet, where management of drainage is going to be possible, or perhaps some other practice will be possible. Lots of design choices and decisions to be made as we work with drainage systems. And of course, I spend a lot of time on all of these in our design workshops. And these are all incredibly important. And another one that I ask people to consider now is, you know, what practices will you also be incorporating into the design, again, to mitigate unwanted effects of our drainage systems? And I'm going to go ahead and answer my own question that all of these options here are incredibly important as these systems are designed. Again, an opportunity to geek out a little bit, but drain spacing is something that, you know, all too often is done sort of by the seat of the pants. And it is an interesting and sometimes challenging concept to come up with, you know, for a particular soil, for a particular design goal in terms of water removal rate, what is the appropriate spacing for that situation? And this drawing is kind of the standard depiction of the components that go into estimating drain spacing for particular soil. And you know, a gentleman, a scientist by the name of Hugout, back in the early 1900s, put soil water theory, boiled it down to a steady state form for estimating drain spacing that looks like this. And so if you're using a tool, an online tool, we'll show you examples of some that are helping you estimate drain spacing for, let me turn on my pointer here, based on hydraulic conductivity of the soil and the depth of water in the soil. They're going to be using this relationship essentially, where you will decide on a drainage coefficient or a drainage rate or a drainage intensity for your particular situation, depending on the crop, depending on the level of risk you want to assume, and so forth. And then knowing this hydraulic conductivity of the soil, and usually assuming 1 foot, usually assuming a water table at 1 foot below the soil surface, allows us to solve for L, which is the drain spacing. And so I just wanted you to see that. Most of you will never see that if you're using an online tool to estimate drain spacing. This is one such tool, and I'll show you some more tools here in a few minutes, but these calculators that Chris Hay and I put together several years ago does incorporate a drain spacing estimation, and it uses that very relationship. You have to come to it knowing, again, the hydraulic conductivity, saturated hydraulic conductivity of your soil, and then you can do an estimation. And so there's no real excuse for for approaching a new field saying, well, I want to put drains at 60 feet or 80 feet because that's what I'm used to doing, or that's what they did right over there, or whatever. The tools are out there now to be a little bit more sophisticated in our approach to this. Again, to kind of beat this concept out, the idea of drainage coefficient, this curve, which is my 0.25 inches per day drainage coefficient, will illustrates the fact that you can have in unlimited combinations of drainage depth and spacing, drainage depth and spacing to produce a desired drainage coefficient for your particular soil. So, we're used to, if you're looking up in the state soil drain in the state drainage guide or something like that, where you're seeing for, spacing and depth combinations for a particular drainage coefficient, and they might list 2 or 3, you need to know that there are an unlimited number of depth and spacing combinations to get to a particular drainage coefficient for your soil. And if we show the other curves here, we see the same thing. Of course, we're getting to be a heavier drainage coefficient as we go down from top to bottom. And this this is going to be important in just a second here as we look at the uniformity of drainage in a field. So this role of drainage coefficient does, when a designer chooses this, it kind of determines the capacity of our system, to move excess water and how the system is going to respond. It's also going to play into crop yield and play into, again, that risk of excess water damage associated with crop production. It's going to significantly impact system cost. As you choose larger and larger drainage coefficients, it means you're going to be increasing, perhaps decreasing the spacing of your system, increasing the feet of tile, and also perhaps increasing the size of the tile. So it's going to affect system costs. And because of that, it's going to affect the net return as well. It's also going to affect water quality. And again, this is kind of a general depiction of what I was just describing there. As we look at going from a wide drain spacing on the left to a narrow drain spacing on the right, we see, of course, the cost of this system is going to go up, like I just said. We're also going to be seeing this kind of big bang for the buck as we go from no drainage to some drainage. But then as you get drains closer and closer together, the benefits are going to become more marginal, and they're going to flatten off here. And what this means then is that the net return that one might experience from the system is going to peak out somewhere, and then it's going to drop off as these annual costs begin to rise, or excuse me, as these annual costs continue to rise, but the benefits start to flatten out. So net returns are going to drop off. So, this suggests that if we knew everything we needed to know about a particular field, we would want to be shooting for some sort of optimum net return here to the producer. I think that just makes sense. As I mentioned, this drain spacing or drainage coefficient also has a very significant impact on the environment. So the amount of water that we drain from the field and associated nitrate and other constituents in that water are going to continue to increase as we decrease the drain spacing or as we increase the drainage coefficient for the field. And so, whereas I think it maybe in years past, it was thought of good practice to kind of err on the side of, having maybe a little bit more drainage than one might need. Now, when we factor in the environmental cost, I think it behooves us to, try to operate as much on the left side of this net return curve as possible. So if I have kind of a flat net return function here, I'd much rather be over here on this side of it than over here on this side, simply because of the environmental cost.
Hey, Gary, we had
Yeah.
a question pop up in the chat there about how drainage coefficients originated and if it was for certain types of cropping systems, and I'm not sure if you can see that.
Yeah, yeah, I'm not scrolled down to the bottom of the chat, but let me take off my. Yeah, drainage coefficients, they were developed in the humid, for the humid region of the U.S. In your, I'm not sure if Keegan, if you mentioned it, but we're going to be providing sort of a binder of handouts and resource material for you. And in there, I wrote up a short piece on drainage coefficients years ago, and you can find them that have been developed for areas all over the world. And it's quite interesting to look at that. But for the U.S., they were primarily developed in the eastern U.S. And they were trying to tie together different types of production, field crops, truck crops or or higher value crops and so forth, and trying to get at that. But that is really just a starting point. It's really just a starting point. I know that wherever you're working and looking at drainage systems, they kind of have rules of thumb. In this area, we like to use a 1/2 inch drainage coefficient, or we like to use 3/8 or a 1/4. Coming up with what the right number is very, very challenging, but it's a combination of, we are managing risk with these systems. So it's a combination of our soils, our landscapes, our climate, and, our what we're producing. And we could certainly take that discussion out longer. I'd be happy to do that sort of offline at any time. And again, reference to that one document in the binder later. So we've seen that drainage depth and spacing sort of combine to give you that drainage intensity or that design drainage rate for a system. And think about that. If the field of interest were uniform soil throughout, we would want our drainage system to have uniform depth everywhere and uniform spacing everywhere, because then we know we're getting the design drainage rate everywhere uniformly on the field. The problem is that, rarely do we have topographies that are easy to work with. They're going to give us some challenge, so that they're going to force us to compromise our objective of having uniform drain depth everywhere. Here's one scenario that makes it very tough when you have fields that are sort of tabletop flat. And I've seen areas like this where, we know we have to put tile on a grade because we want water to flow from the high end, to the outlet. And when you don't have any natural grade in the field, even when tile is put at minimum grades, you're going to end up with shallower on one end and deeper on the other end of the tile. And if we go back to our figure here, for that very example, if we went from 4 to 3 feet over that, what was it, 1,000 feet of tile, we're actually moving for this particular soil, from a 3/8 drainage coefficient down to a 1/4 inch drainage coefficient, just over the length of that tile. And if my soil is uniform, why would I want that? Why would I want a light drainage coefficient on the high end of the field or a one end of the field and a heavier drainage coefficient on the other? I would rather it be uniform. And so that really is the challenge of designing a good drainage system, is trying to get at that uniform performance throughout the field, given the topography that we've got in any particular situation. So here's again, kind of that same situation, an even longer field. We have this long rectangular field, 2,000 feet long. If we had laterals that were 2,000 feet, at minimum grades, 0.08%, you could go flatter, but it's hard to go even flatter than this. Even at a minimum, you've got about 1.5 feet difference in depth on these laterals from one end to the other. If you weren't able to install tile at that flat, let's say you're using a pull behind plow or something, you can't go 0.08. 0.1 is probably the lowest grade you can do. You can have 2 feet of difference from one end to the other. So if you were at a 3-foot depth on the high end of the field, you'd be at a 5-foot depth at the bottom end of the field. And that's just too variable of a drainage coefficient. If you ask me, if I'm trying to treat the field uniformly, I think that's too much variation. So you can solve that by splitting the field in half. And so now we're going to chop, if laterals were at, again, that 0.1, instead of a 2-foot drop from one end to the other, we're going to break it up into 1-foot drops on these two different parts of the system. And so think about imagine topography in your head, and think about a network of pipes below the soil where you're trying to minimize the variation in depth to get the system all performing in the same way. And now add on top of that the fact that the soil is not uniform throughout the field. The soil changes. And so it throws another factor in trying to get this sort of uniform performance across the field. It's quite a challenge. And it's one reason why these computer tools for doing drainage layout are so powerful. In fact, we developed a drainage design tool back in the 1980s, before many of you were born, I'm sure, that would allow us to bring in topography information into the computer. Yes, we had computers in the 1980s. Bring topography information and put a tile network on that field, and then actually optimize it for a particular depth that we were seeking for that design. So the problem is sort of well suited for computing. But what do we give up when we do this? This system is more expensive than that previous system where we had 2,000-foot laterals. So there's going to be an increased cost here. So the designer has to pitch this to the client that you're getting a more uniform performance out of your system at an increased cost. Does it mean that you're going to do this with no limit on what you're going to spend? Of course not. Everything, there are compromises to be made all along the way here. Another rule of thumb that is going to factor in strongly to our discussion today is this idea that we're always going to be better suited in putting our laterals more on the contour rather than up and down the slope like we see here. But I will say that putting in tile this way, as I'm showing on the right, is easier to do. When you are, you can go out into a field and install tile on the fly without even evaluating the contours. You can do everything in the field. if you are putting tile up and down the slopes. You can maintain constant depth, again, to a point, not for extreme slopes, but it's easy to do this, and I see why many contractors have done this over the years. On the left here, though, with laterals more on the contour, these laterals are going to do a better job at intercepting water as it moves down from high to low in the landscape, in the field. But also we're going to see later that that's going to be crucial for doing drainage water management. It's going to be crucial to have laterals more on the contour. I won't say much about drain sizing, but it's kind of that last step that the designer does based on that desired drainage coefficient or drainage rate. They're going to be, you can look at any one pipe that's out in the field and kind of look at this chunk of water that has to move through that pipe. The height of this is really the drainage coefficient, 1/4 inch, 3/8, 1/2 inch. And when you multiply that by the area that you're draining with that lateral, you can compute a flow, and then using tools, then you can figure out how big that pipe needs to be to move that amount of water. You're going to do this for every pipe in the system, and that's kind of the last step that the designer is going to do. Topo maps is crucial to understanding, to doing good drainage work, but even more important to doing drainage water management work. And so I want to just spend a second here looking at topographic maps. Let me just say that for those of you who are not used to looking at these, I don't have any labels on this. I don't have contour elevations labeled, but each one of these lines is a constant elevation. Okay, that's what a contour map is, constant elevation. And I'm going to tell you that let's see here. This end of the field is the low end, and this end of the field is the high end. So higher elevation up here on the top, lower elevation on the bottom. So with that in mind, I want to ask you, this feature right here that we see, where the little curves here are kind of pointing uphill, what is that feature? What is that feature? Go ahead and throw something in the chat. I see a waterway. Hang on, when I have my pointer turned on, I can't look at the chat. It's a channel, it's a gully, it's a waterway, it's a channel. Right. So where the curvy lines again are pointing uphill, that is a draw. So conversely, what is this feature where the curvy lines are now pointing downhill? What is that feature? A hill, high ground. It's a ridge. Yeah, it's a ridge feature. So those are two things that you can keep in mind as you look at contour maps, and you're gonna be looking at them today, and you're gonna be looking at them a lot. If you do work in this drainage water management area, you're gonna need to be comfortable looking at contour maps. The problem with contour maps is that they are 2 dimensions. They're 2-dimensional. And so you can't really see what's going on. But here's an example of a contour map in 3 dimensions. rice farmers in Asia have a nice display here of a contour map. And it's a terrace rice field. And as you look here, of course, here is your curvy lines pointing uphill. That's a draw. And here are your curvy lines going downhill. That's a ridge. So really easy to see when you see them in 3D. If you don't have any elevations on the map, if you don't know how to read those two features, you're going to look at this and not know if that's a high spot or a low spot if you're not reading those other features well. Of course, once we put some elevations out there and label things, that's going to help us greatly. Now we have access to incredible data to get really high quality contour data. And I think LiDAR is probably out there now in most of your states. If it's not, I'm sure it's coming soon. We have access to that in Minnesota and Iowa and South Dakota, North Dakota. And these are just different views of generating contours from that LiDAR data. And this is going to be, of course, much more refined than the old USGS quad data that's out there. Those are great for planning purposes, but when you really get down to the nitty-gritty on a field scale, particularly in fields that don't have as much relief in them, you're going to need to go better than the old USGS quad maps. So again, just different ways of looking at that elevation information generated from LiDAR information, LiDAR data. These colorized maps are really interesting, and they might be useful as part of a package, for your client, but they're difficult to design from just a colorized map. So you really need to add some contour lines there, particularly for drainage water management, so you can see what's going to be happening in your system from one elevation to the next. Again, just more examples here of contour maps developed from LiDAR data. So I mentioned that there are a plethora of design tools out there running the gamut from the old nomograph on paper here, which I love, by the way, to design tables that are in various state drainage guides and NRCS drainage national handbook. There are handheld tools, slide charts. We developed this one years ago with Prinsco that has seen a lot of use and is quite handy. There are online tools as well that are out there, and there are more than I'm showing here. I think, Keegan, have you got a couple of examples of online tools as well?
Yeah, and I just kind of show some examples here real quick. Let me share my screen. And, pretty basic. I'm getting into PowerPoint. But kind of what Gary mentioned, these drainage design tools, all pretty intuitive, I would say, if you get to them. There's anything, you can get your pipe size calculator, see how big of a pipe you need to drain an area, or you can see if you have a pipe size in mind, what your drainage potential is for that pipe size, for how big of an area that would cover. If you go look at a lot of the pipe manufacturers, so members of ADMC, they all have a form of these tools on their websites. You can go to them and visit them there. ADS, Fratco, Prinsco, and Springfield Pipe all have these available. I will say for our Extension University friends here, and I have one example, maybe if you guys have links to your own tools, feel free to drop those in the chat. Michigan State, I really like the way they have theirs laid out right now. That very first drain spacing tool on the Michigan State website is interactive and actually has a little bit of a profitability analysis calculated into it. And so right now it's only coverage in the Midwest as far as the soil types, but it does factor in the soil type, so you can lay out your area of interest, just like how Gary showed with the web soil survey on that. You can factor in some other considerations if you want to go advanced, like anything from cropping price to your depth of your expected water table. But that drain spacing tool will then tell you how wide that layout needs to be. And then, I'm sure Gary will mention it, but sizing that main is one of the most important things to do when you're considering these drainage layout systems. That's kind of one of the leading factors, I would say, in underperforming drainage systems is under designed mains on these. So a lot of these tools, you'll see that main sizing, and once again, very intuitive. This Michigan State website, Hassan Gagne has some nice videos linked to it where he can explain them kind of step by step of how to use it. But if you go around, search for maybe your local university extension website and drainage, I'm sure you can get to a lot of these. Then I'll turn it back over to you, Gary.
Thanks, Keegan. And I mentioned this, the iGrow drainage calculators before, and you see a lot of different functionality in here, all the basic stuff you would need. And of course, these will also pull up on your smartphone or your tablet and format accordingly. Once upon a time, I hope this is still out there. Richard Cook's Illinois Drainage Guide had a really nice interactive nomograph. So for those of you who really want to geek out, this is a great way to really look at trade-offs between pipe sizes and slopes and so forth. Very, 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 very useful. You can also add in here a degree of sedimentation in a pipe and calculate size based on that. Very helpful. Lots of drainage publications out there, looking at all manner of issues, design, and so forth. And I know the Transforming Drainage Project, I'm not sure if we've got a slide to plug that, but we're going to be talking about some of those resources as well as we go through the day. And to end this first session, I'd be remiss if I didn't mention safety as you get out in the field, whether you're a researcher out there doing field work or you're a contractor or whatever it is. If you are in the field and involved in drainage, it usually means you're working below the ground surface, trenches, holes, and so forth. Cave-in related accidents are much more common than one might think, and a pretty high percentage, higher than many other construction accidents, result in disability and death. In fact, we just had one here in the Twin Cities a couple weeks ago, I think it was. Somebody was working in a very deep trench. I have no idea of what was going on there, but a young man died with a cave-in. So very, very dangerous work. I'm probably guilty of not taking enough precautions in some of the research work that I've done in the field. And so I really just want to emphasize to all of you that to really don't ever take for granted, that a trench is stable and just jump down in there to do something. Really use the best trench safety practices, and you all know what they are, at all times. Just because it's a quick connection or something fast doesn't mean it's safe enough to do. So I really want to underscore that. And of course, call before you dig. That's another important thing. That is the end of our first session.